Hey. All right, go ahead and pull out Evolution of Populations Part 2, and you'll see that this is a short lecture, so it should be a pretty short video. Yay for that. Okay, so Hardy-Weinberg is a set of equations, or a set of, it's a formula, and what it does is it measures evolution. It puts a numeric value on evolution. So your notes say a set of equations used to follow the evolution within a population. And so what Hardy-Weinberg does is it measures evolution. So instead of just being like the population did evolve, you could say, well, it evolved this much. And so it's just a measurement. I'm actually going to use my whiteboard most of the time. Okay, so if the numbers do change, and we actually kind of talked about this before, I told you about the capital A and little a, and if that's 0.5 and that's 0.5, well then, if it continues to be 0.5 and 0.5, then there's no evolution, if it continues that way. And if it changes, like let's say 0.4 and 0.6, well, then there was evolution. And so let's look at how do we determine the numbers. How do we work out those problems? Okay, and so it says the first equation, well, let's start with this. From now on, instead of thinking of capital letter and lowercase letter, I want you to think of a P and a Q, where P is the dominant letter and Q is the recessive letter. Okay, so, or maybe I should say allele, not letter. Whoops, that was bad. Dominant allele and the recessive allele. Okay, so from now on, P is capital A and Q is lowercase a. Well, if you add up all the P's and all the Q's, well, then that's going to be 100%. Well, yeah, all the dominant alleles plus all the recessive alleles, well, that's 100% of all the alleles. Not a very impressive equation. Okay, the second formula says that all the people that are, and you want to write this down, homozygous dominant plus all the people that are heterozygous plus all the people that are homozygous recessive. Well, that's 100% too. And so make sure you want to write in, this is homozygous dominant plus homozygous recessive and this one is heterozygous. Okay, the reason it's 2PQ is because there could be big A, little a, or there could be little a, big A. So there's two of those. Or it could be, PQ or QP. And so all the people that are homozygous dominant and all the people that are heterozygous and all the people that are homozygous recessive, that's all the people. That's 100% of the population. And so it tells you what everything stands for. These equations are mainly used in health science to explain the frequency of genetic conditions. So if most of the population used to have been 2PQ, and now most of the population is Q squared, well then evolution occurred. And so let's practice real quick. And I actually want you to write this in. When you're solving this, there's a couple rules I always want you to follow. So number one, always solve for Q squared first. That's the first thing you want to solve for, because you can't tell much about the heterozygous and you can't tell much about the homozygous dominant, because if you'll remember, big A and big A, little a, they look the same from the outside, but little a, well, they have the recessive trait. Okay, so looking at Q squared is going to be where you always want to start out, and then if you know Q squared, then how could you solve for Q? Solve for Q. Well, I mean, that's pretty easy. You take the square root of Q squared, and that's going to give you Q. Okay, then if you do 1 minus Q, that's going to give you P. Because remember the formula, P plus Q equals 1. Okay, so now that you know P, which is the dominant allele, and you know Q, which is the recessive allele, all you have to do is answer the question. And you can answer any question they want. What's the frequency of someone who's homozygous dominant? Well, that's going to be P times P. What's the frequency of someone who's homozygous recessive? Well, that's going to be Q times Q. And so from here, you can answer any question. So let's try one real quick. We'll just make one up. Okay, if there is, let's say there's a population of 100 people. And we'll say that out of the 100 people, 50 people show the recessive trait. So that would mean that 95 people show the dominant trait. So 95 people are either P squared or 2PQ. These people must be Q squared. Okay, so remember you always want to solve for Q squared first. So 50 divided by 100, well, that's going to be Q squared. Okay, and so that's the answer to Q squared is going to be 0.5. Okay, how do I find just Q now? So I've got Q squared. Q must be the square root of 0.5, which is 0.7. I'm looking at a calculator. Okay, and then how do I find P? So that's always next. P equals 1 minus that, so that's going to be 0.3, right? Because if I do 1 minus 0.7, it's 0.3. And so I want to know what percent of the people are homozygous dominant. And so if I want to know that, all I have to do is homozygous dominant. So P squared equals 0.3 times 0.3 is going to be 0.09. That's P squared. That's the frequency of homozygous dominant. Q squared I already know is 0.5. And then what's the frequency of people that are heterozygous would be 2 times 0.7 times 0.3. And that's 0.42. Oh man, I could have done that in my head. So 42%. Okay, so now go back to your notes, flip back there. And so there's 5 things that if a population is in Hardy-Weinberg equilibrium, that means there's no evolution. That means there's no evolution if it's in Hardy-Weinberg evolution. And so there's 5 things that could make that happen. 1, it's got to be a large population. It's got to be a large population. 2, nobody's moving in, nobody's moving out. So we're going to call that gene flow. Nobody moving in or out. 3, nobody can be mutating because mutations lead to evolution. Random mating, it's got to be random. The peacocks can't be just choosing the pretty peacocks. Okay, and then so it's got to be random mating. And then there can't be natural selection because natural selection leads to evolution. So gene flow, mutations, and natural selection, they lead to evolution. Mutations lead to evolution. Random mating If the mating is non-random, well, that would cause evolution. And you want to know that small populations evolve faster than large populations. So if a population isn't evolving, those 5 things must be being met. All right, I hope this was helpful.